All right, so for students who are in integral calculus, and especially who have already seen the idea of using Riemann sums and all that, then you must have seen how important the idea of being able to sum up, and create a lengthy sum to accumulate an area. And so that is the reason why I decided to write this lecture here, where you have seen the idea of how to use summation notation before in one of your algebra course before calculus, but here allow me to in this lecture to allow me to deliver the more advanced kind of problems. So here the title of our discussion here, the title of our lecture here is the summation problems in calculus. So I would like to introduce the kind of examples where you probably have not seen that in in algebra course before, but here I would like to I design these examples so that calculus student will have a direct experience, so that when you will apply the skill of the summation problems back into your calculus problem, integral calculus problem, especially on the Riemann sum idea, right, then your work will become a lot easier. And but even so, even though I mentioned this, even though it seems that like I wrote this lecture to aim at the viewers who are in integral calculus, but pre-calculus students are always welcome, or even algebra students are always welcome to view these kind of problems, because you must have done some basic, at least some lessons about what summation notation is. So these problems, once you view it, it will be a good foundation for you, so that later on when you go to your actual calculus course, and particularly the integral calculus course, you will see a lot of usefulness from these problems that I designed here in this particular lecture. Okay, and so in that way, how I explained then allowed me to pick up from the point where I assume you already know what a summation notation is, and at least you have been fluent enough with how to write a sum into a summation notation, and understand what it is. But now we're gonna take on from the next step here, where I deliver somehow a slightly more challenging problems, and more advanced kind of problems, so that it's more directly related in your calculus study. Okay, so here we go. So now in your understanding, allow me to bring up a demonstration problem that motivates the idea right here. So now you know what it is about summation notation like this. Okay, and so assuming you already know what a summation notation means, then if you're looking at a sum like this, that means writing down the sum like this. It means so this summation notation, as a brief reminder, it means we're summing up all the terms. So first term, so this index right here is indicating that the first term, so the first term has value determined by this formula. I mean any term at any index. So this is an index. Okay, so any term at any index has the value determined by that index value. So first term here for this sum is a 1, and then it's a summation. So next term here we're adding 2 to that, because see, at any index value, then our term at that particular position is determined by this particular formula, and our simple formula here is the I. So term 2 is 2, term 3 is 3, and so in the way how it is, and again assuming you already understood that the basic enough summation notation, then this means our sum here, once we write down all the terms, it will end, and see, it's gonna start getting lengthy. So I'm not going to write all the terms down, but I'm gonna leave dots between a couple plus signs here. So we add, so 1 plus 2 plus 3, and we keep adding until the last term here is 10, and that's what this superscript 10 on top of our summation notation is for. Okay, so this is just a way of writing it. We're writing the lengthy sum here in summation notation, and so summation notation is, from your algebraic understanding, it's just a way to represent a lengthy sum. So instead of writing down all the terms, we use a more condensed form of a summation notation to write this sum in a more convenient way. But in the end, the problem I want to introduce now is that if we now really want to add up all these terms and find a final answer, because in the end, the whole purpose of doing a sum is to eventually add up all the terms right here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 are all being hidden in these dots right here, and then plus 10. So really we have 10 terms here. The question now is that how are we going to quickly add? I don't want to sit there and go through my calculator. 1 plus 2 plus 3 plus 4. We don't want to do that, even though it will work. If you want to find a final answer, I'm talking about a final total up of all these 10 terms right here, then we're looking at some kind of value. But we definitely don't want to go through, well, 10 terms is not so bad for now, but later on, what if we have a sum like that, similar bit, runs 20 terms or 12 terms or more, then we're going to take a lot more time. So now here's the thing. Well, to illustrate the idea, see it, if we really adding, then it's 1 plus 2, that's gives me 3, okay, and then 3 plus the next 3, that gives me, and then keep adding. If we have to do that step by step like that, by adding up all the terms, and 3 plus 3, now that 3, so the first 3 came out from 1 plus 2, and then we add 3, that's 6, but now adding with all that 4, 5, 6, up to 10, see? And I didn't even get to the final answer yet, but work is starting to get long. And so 6 plus 4 right here is a 10, and we're going to continue adding. And so it's already, we can already sense that it takes a lot of time, that even I've been teaching for years, I just don't want to get anywhere near this kind of work here. It takes way too much effort for us. So there has to be a way. So we still want to get to the final total sum, but we just want to find a way to quickly get the answer. Okay, so ladies and gentlemen, here's how I see it. So this way that I wrote down, that I suggest, that we tried earlier, didn't work out too well, because the problem here is we're adding too many terms. We're having too many terms to add. And then be ready for the case where, what if we have 100 terms, and then good luck with that. Okay, and so here, the observation here is telling me that, and it should be the number 10 up here, it's indicating that we have, in the end, when we really writing it down, we have 10 terms. First term is here with index 1, so this is a summation that starts with term 1, that we're adding from term 1 all the way to last term. And so now that means if we're really starting from first term and ending up with 10 terms all together, so this number means we have 10 terms. Okay, we have 10 terms, and that also means the last one here is the 10th term. Okay, and so here's the way how I can quickly get this total sum, and believe it or not, we will get there. Okay, so 10 is the last term, the value on the last term. Okay, 10 is the value of the last term. I am going to multiply that with, so the last term here, I mean in this particular term is the 10th term. Okay, we got 10 terms, and the value on the 10th term is 10. Okay, and then we're going to go times 11. Okay, and then I'm going to divide it by 2. Okay, and we are already so close to the actual answer. So with this work I'm doing over here, now 10 can quickly, and before I pull out my calculator, 10 can quickly cancel with that 2 right here, and that gives me 5 times 11, and so 5 times 11 turns out to be 55. Okay, so 55. Now, so here I want you to verify this answer of mine by really adding 1 with 2, and then whatever that sum is, add 3, and whatever that sum is, add 4, whatever that sum we get currently, add 5, and keep adding until you reach the last one. Your answer will also be 55 right there. Okay, you can feel free to pause my video at this moment right here and go ahead and verify by really adding up all the terms right here. So the point now is that we have a lengthy sum, but we have found a way to quickly get to the final sum of all these terms together, but without adding all the terms together. So we calculate the actual value of the whole lengthy sum here without adding the terms. Okay, and so that was the quick formula. So what was that formula that what generality that I found for that quick little work like that? So it looks like so far in the generalization that we have understood, that we have picked up just now, that we have just learned now, then when we're looking at a sum that start from first term, and each term takes value equals exactly the index position of that. So this means 1, right? Sum with 2, sum with 3, sum with 4. Okay? First term, second term has value 2, third term has value 3, fourth term has value 4, and keep adding, etc., to some generally nth term. Okay? And so again, as I explained earlier, this general superscript on top of the summation notation here means that we will end up with a total of n terms. There will be n terms. There will be n terms, or alternatively, you can understand as this last one right here, n is the nth term. Okay, because the formula here I'm about to write down, I'm about to generalize, is only for the kind of sum where it started with, the first term here is at index 1. So we're always going to start our sum with index 1 and then ending at some n term like that, or ending up where we already have n terms. Okay, and so the general what we have recognized through the demonstration problem earlier is that this adding right here, without adding up the terms, without adding up n terms, that's too much right there. Then our quick answer for that was, see, the 10 was generally an n. Back in that demonstration example I've done earlier, and then I multiply with 11. So 10 multiplied with 11. So it looks like as far as the value, 11 is n plus 1. So n right here, because in this particular problem, n is 10, and then 11 here is 10 plus 1, or n plus 1. And so now I can generalize that by, we simply just, the value of the last term, or just the number of terms, actually, to be more precise, the number of terms multiply with n plus 1, okay, and we divide it by 2 right here. So now we have generalized for ourselves one important formula. This summation, this famous summation, the sum of all I terms from 1 to n, okay, can be quickly summed by this shorthand formula. Okay, I wouldn't call it, it's a shortcut, but it's a really nice shorthand formula that completely bypasses adding up all the terms like that. Okay, and so as a quick demonstration, demonstration of the usefulness, before I get into any formal examples, then see, when we get to from I equal from 1 to 20 right here, that means now having to write down the terms or not, that's pretty much your choice, but this sum here means 20 is the last term, or the number of terms right here. I'm going to multiply with 21. Okay, so the value of the last term times the next one over, and I'm dividing that by 20. So 20 already divided by 2 right here. And then you can see that 20 will cancel nicely with 2, giving me a 10. So 10 times 21 is a 210. Okay, and you can always pause the video lecture here to verify for me by rewriting this sum as a 1 plus 2 plus 3 plus 4 plus, and keep adding until you reach 20. That sum right here, that lengthy sum, will equal 210. Okay. And so now, that was one among the demonstration problems I would like to bring up. So we're looking here at a summation of where each term is having a value precisely equal to the index position where it's currently at right here. So term 1 is 1, term 2 is 2, and adding a lengthy sum like that, we just now arrived at a general formula. So now we're going to start getting a little more advanced right here. Alright, so what if we're looking at a lengthy sum like this? First term is a 1, okay. Second term is a 4, so second term, term 1, term 2, but the value here is 4, okay. Term 3 is 9, term 4 is 16, okay, and then we'll keep adding. So you start recognizing a repetitive pattern in these terms right here. So first term, second term, third term, and I intentionally break it down this way so that you can also reveal your skill in terms of how you can recognize the summation formula for that, the summation notation for that. So first term is here, second term, but value 4. Third term is value 9. Fourth term first, second, third, and fourth. So index 4, I equals 4 is here, I equals 3 is here. That's what I intend for. And then you start recognizing a repetitive pattern, and then we keep adding that until whichever position that has the value being, so I equals something that has last term being 100. Okay, and so in this term, in a sum like this, needless to say, and of course, again, just like how I explained earlier, this video lecture here is intended primarily for the calculus students. And so calculus students already have, a good enough majority, a high enough majority to quickly recognize this. So you can see that each term here is the square. So this is the square of 1, this is the square of 2, this is the square of 3, and so on and so on. So each one of these numbers now is associated directly with the index of the index position of the term right there. So in that way, this is clearly a summation of all the terms where it's an I square in each term like that. Okay, it's an I square, and yes, we're summing from first term I equals 1. But then, so who's it? What's the last term here? I mean, how many terms do we have? How many terms? What's the number we put here? How many terms do we have? So it looks like back in this actual sum right here, the last one in our sum right here is a 100, and it looks like in this rule we have recognized it looks like it's a 10 square right here. So it also tells that in this sum we have a total of, we have a whole 10 terms together. Okay, when we keep adding up all of those terms, so that means our ending index here is a 10 like that. So so that's how we come up with the summation notation like that. Okay, but now again, the exact same kind of problem that I introduced earlier, I brought up earlier, we definitely don't want to add up. See, adding 1 plus 2 plus 3 plus 4 was already so much problems. It got lengthy to the point that we just didn't want to add up all the terms, so we had to come up with a quick formula. So same thing here, we definitely want to stay away from adding up the terms here. So is there a quick way to bypass? I mean, is there a quick way to find the actual sum but without adding all these terms here? Okay, and so yes, there is. So now here's what I'm doing. So allow me to introduce this lengthy sum without adding the terms. You're going to end up with, you're going to multiply that 10, the number of terms, okay, multiply with 11, and start recognizing how these values are related with each other. And then this is 21 right here, okay. Of course, I will explain where all of these values come from, but we're going to divide by 6. Okay, so as far as I'm concerned, the 21 has a common factor 3 with 6 right here. So it will cancel, give me a 7. And see, I'm doing it live, so I didn't have a calculator prepared here with me. So that cancels by the 3 away and leaves me behind a 2. The 10 has a common factor 2 right here, so that cancels, leave a 5 behind, so that cancels with this. So in the end, we're looking at 5 times 11 times 7. And 5 times 7 is 35 times 11. We're looking at 385. I put in a lot of explanations through the steps to arrive at this final answer, but I highly believe I'm still getting the final answer here faster than whoever going through 1 plus 4 equals 5, plus 9 equals 14, and so on until you add with the last term being 100. Okay, so there you go. 385 is the exact answer to, adding up all of these terms here to arrive at 385. Okay, so what was that formula what was that secret formula that seems like I was hiding it, but now I'm about to tell anyone? All right, so as a generality, the summation we were looking at was the summation where each term is the square, is the I square term right there, where we're starting the sum at first term and we're ending the sum at some general end term. And so this means writing down the terms, it looks like as following. Term 1 is value 1, term 2 has value, see, position number 2, but it has index. It has index 2, but it has value 4 because 2 square, I square. You see the value of the term is governed by a formula that's dependent on the index of the term itself, like that. Okay, and so term 3, third position, but the value of the term is determined by I squared. So here we're looking at 9 plus, and generally when we reach to the nth term, the index position reach to the nth term, we're looking at n squared, right there. That's the value of the nth term, right there, when I equals n. Okay, so that's the written out form. It's just a written out representation of the sum. But now to quickly add that sum, and in the end, this sum still has n terms. Okay, it still has n term. The last term is the n squared value. But here's the work. So the quick way to add all of this without summing up all the terms is going to be n. For n terms, I'm going to multiply with n plus 1. And that's why it was 10 times 11, as you saw in my other board earlier. And then the reason I had a 21 here as the next factor was because it was a 2 and plus 1 there. Okay, and that's how I got that 21. And then, so after the product of these 3 little factors together, the formula that was proven was divided by 6. Okay, so I'm introducing these formulas. At this point, I'm introducing these formulas without providing a valid proof, because these formulas are quite standard and quite a common understanding throughout many standard pre-calculus textbook or algebra, or even, calculus textbooks or pre-calculus textbook or even algebra textbooks. So I don't need to deliver a proof here that just take away your valuable time learning. But you can always open any textbook that you have that was assigned to you, or you have to see in the back of that, there has to be a page somewhere that proves these formula, okay, to derive how past mathematicians come up with these. But now we learn these formulas and understand what their purposes are, okay, and that's the only purpose of these formulas, and then we're gonna learn how to use them, okay, and that's the whole intention of this lecture over here. All right, so with a problem like this, that's how, with that generalization, that's how I was able to quickly calculate this. And I was not using a calculator in front of the camera at all. And you can see that how convenient it is to know and use these quick formula to bypass adding up all the terms for any summation problems. Okay, and so now you have learned the formula for, so let's recap what we've been doing. Earlier I introduced that famous summing up all the terms where each value of the term is directly I right here. So this means 1 plus 2 plus 3 plus 4, etc. to the last term. Okay, and that's final formula. That final quick way to add up all the terms to get the final sum is n times n plus 1. Okay, divided by 2. So just for you to know, in case your textbook didn't tell you, but it was Gauss who came up with this formula. Okay, and I believe that was when he was at the age of either 5 or 6. This is the part where I doubt my own memory about this, but he came up with this. This famous mathematician of the whole history came up with this formula when he was at a very young age. Okay, so we've learned that now. We've learned this. And just now we've learned, so when it's the summation of the I squared term, on each I squared term, when we're summing from 1 to n right here. Yes, our terms are looking as follow, and 1 plus 4, because 1 squared plus 2 squared plus 3 squared, now it's 9, plus 4 squared is 16, and keep adding until we reach some n term, which is n squared as a value of the particular term. So that here, the quick. Now this term, this particular formula I'm writing down right here. I'm not sure if it was Gauss who invented this, but Gauss was the one who had this first one. But it opened a door. It opened a door for people to hunt for these other quick formulas. At least if it wasn't Gauss, and Gauss was the first one that opened that door for other mathematicians to hunt for quick formulas to get this. To get these other formulas that you see in these days throughout standard calculus or pre-calculus textbooks. Okay, so it was n times n plus 1, okay, times, and maybe my board space is a little too short, so now how about I'm writing it down here, n times n plus 1, just like what I wrote on my other board earlier, okay, and all over 6. And now you can have two quick, handy formulas to look at. And so outside of these formulas, there are a few other ones, but not as commonly used as these two right here. Okay, so let me introduce another one. All right, so if we're looking at something like this, we're having a sum of the I cubed right here, where it's a summation of all the I cubed term from first term to the nth term right here. So we're still having n terms, but each term value is an I cubed. So what's going to happen? What's going to be the final answer when we finally come up with a sum, but without adding up all the terms right there? So now I'm just gonna get straight into the point right here. As far as the terms, the values of the terms are 1 for first position, because 1 cube is 1, 2 cube is 8, 3 cube is 27, and I'm running out of space here, so I'll just quickly leave dots here, and then wherever the nth term is, it's n cube. That's the value. But now the quick answer, the quick formula that brings you right into the final answer is going to be n squared times n plus 1 squared divided by 4. Okay, that's one way of how you're seeing this formula. Some textbook in these days, some calculus or pre-calculus textbooks in these days write the formula as the following. Maybe their intention is to make it click better for students to remember. But if a summation like this, and especially when we're looking at this final formula, it seems like, or it looks like it is the n times n plus 1 over 2. Recognize this? This was from the summation of all the I terms, no power. But then we're going to raise that off and final answer to the square right here. Okay, so that's another way of explaining this. Right. But you can also take that summation of all the I cubed terms to equal to the n squared times n plus 1 all squared over 4. Yeah. Okay, but outside of these three formulas that I introduced on the board right here, probably because there haven't been too many applications of those other ones. So that's why I haven't seen too many of those. But these are the most common ones, especially the summation of I and the summation of the I squared. Okay, so those are a few of the quite famous ones. That's the purpose. Again, only one purpose. These formulas help you come up with the final sum, the final calculated sum without adding the terms. Okay, and that's the purpose of these any of these formulas. So now allow me to start getting into some actual example, and again, my purpose here is for my calculus students or even pre-calculus students. After you learn about what the summation notation is, then you can gain the better experience by going through these slightly more advanced kind of problems, kind of examples. All right, so let's look at example 1. So the instruction here says we want to calculate. Okay, we want to calculate the following sum. Okay, so expect that after this instruction of the problem, I am going to give some kind of sum right here. So calculate the following sum, but the requirement here is without, and that's just directly out from what I have been introducing to everyone. So without adding, okay, the terms. All right, so without adding the terms. So I don't want to go like in that demonstration I've made earlier. I don't want to go 1 plus 2 plus 3 plus 4, and that's way too much time for us. All right, so now the summation we're looking at here is, how about part A right there? How about I, where we're summing from first term, okay, to the 36 terms. 36 terms, okay, you know, definitely, and each term here has value determined by just simply I. So term 1 is 1, terms 2 is 2 for the value, terms 3 is 3, Okay, and so on and so on. So well, this is just writing it down. Term 1, terms 2 is 2, terms 3 is 3, term 4 is 4, and keep adding until you reach the last one here is the 36th term, where it has value 36. Okay, but now how are we going to sit there and add up all of these? We definitely don't want to pull out a calculator and 1 plus 2 plus 3 plus 4 plus 5 and so on up to 36. And so now the quick formula here that we have learned just now, this is going to be now, and in this case is 36 right here. There are 36 terms. I'm going 36, okay, times n plus 1, which is 37. Okay, or maybe I shouldn't rush anyone, so I'm going to write it down in a more explain out way right here. So 36 times 36 plus 1. So where did that 36 come from? It's the number of terms, or just the index of the last term like that. Okay, and then we're dividing that by 2. So this is just straight with that formula I have introduced just now. And so of course 36 plus 1 is 37. It won't cancel with 2, but 36 has a common, 36 itself here has a common factor with 2, so we cancel that, and that leaves me 18 right here. So here we're looking at 18 times 37. Now we can use a calculator to get the answer, and it should be a lot faster than going through and adding from 1 all the way to 36. All right, so the final answer here is 666. Okay, and you can always double check my work here by pausing the video, and of course if you want to, you can also double verify by adding up all these terms if you are patient enough with that. Okay, all right, so let's look into another problem. We're still in example 1. So how about part B of the example? Let's look at the summation where each term is an I square, and we're summing from first term to the 20th term. So in other words, we have 20 terms altogether. If we're writing it down, all the terms, I mean, it's not always required. The problem itself did not require. So when you're actually doing a problem like this throughout your assignments, writing down the terms or not, it's pretty much it's on your choice. Okay, and it all depends on any extra details, any extra instruction on the problem itself. But for this particular problem right now, it's not required to write down the terms. I'm just writing it down, to give extra clarification. So term 1 is 1, term 2 is 4, because 2 square is 4, plus 9 plus so on and so on. My last term is a 20th term, but 20th term is supposed to have value 400, because 20 square is 400. Now good luck adding up all the terms. It might sound funny that I said good luck adding up a term, but that's the point. We don't want to waste our time adding up all the terms like that. Okay, so what was the formula that we've learned earlier? We know that we have 20 terms. That's what this 20 is for. So 20, according to the formula, times 20 plus 1 as an extra factor, part of the formula that we've learned. Plus, need to correct that, times 20, about 2 times 20 plus 1. I'm really writing down the formula with the proper number plugged in and to redisplay the formulas there. So this means we're looking at 20 times 21 times this is 41. Okay, and we're dividing that by 6. Okay, and so just like how I explained in when I was doing that demonstration problem, 6 has a common factor with 21, so cancel that. We're gonna have 3 as a common factor with 6, and so we have 2 left in the denominator and 7 left for that 21 after canceling the 3 away. And then 20 has a common factor 2 with this 2, so 20 cancel away the 2, give me a 2 remains, and then that 2 cancel, leaving a 1 at the denominator here. All right, so now it looks like we're doing 7 times 10 times 7 times 41, and it's all commutative. So that's 7, and that's 287 times 10, so 2,870. Okay, and that's your final answer right there on that. Okay, So that's, if we're looking at closely at the instruction of the problem, see, the intention here is we want to get and look at how fast that is. And I already gave so much explanation with it. I highly believe it should be faster than typing all these terms in a calculator. And that's the whole point of this kind of problem right there. We want to know these formulas so that we can quickly calculate the sum, that sum, without adding up all the terms. Okay, so that's not all for the examples I would like to deliver. So let's get into example 2 right here, where we're going to allow the problems to grow a little more advanced like that. Okay, so now I'm going to erase the work here. And let's now call that example 2. The instruction of throughout the entire example 2 stays or remains exactly the same. We're going to call it example 2. We want to do the calculation. We want to calculate the sum without adding the terms. But here's, let's look at the sum right here. So part A, how about in this time the sum is not written out, it's not written in summation notation. It is us who need to recognize. So that's the next kind of challenge right there I want to put on top of example 1. So the sum we have really is a lengthy sum, 1 plus 2 plus 3. I hope as I'm writing it down, viewers to this video lesson start recognizing the repetitive pattern so that you can be able to write this down into your summation notation. Okay, plus 4, keep adding that until we hit to 100. All right, so what sum is this? What sum is this? So it looks like a lengthy sum like this. And by the way, see, this is term 1, term 2. These are all the terms being listed down, and we will never have enough paper space to write down all the terms. That's why I'm leaving dots between some 2 plus signs like that. But then the idea again, we want to calculate the sum, but definitely without adding the terms. We don't want to add term by term like that. Okay, and so now just by observing the first few terms, we can already start forming it into a pattern right here, because we need to be able to arrive at the summation notation, the summation notation representation. Okay, so term 1, index 1, this is I equals 1, this is I equals 2 for that one. Okay, and I equals 3 for that one. So it looks like each term, the value on the term is I, right? Is exactly equal to the term indexed position. And so that means it's a summation of all the term with value I, where I does start at 1. And like I said, any of these formulas I deliver today always work on those summation where it starts with term 1. So that's one thing we can always guarantee for us. But then what's the last term? Or in other words, how do we find out how many terms all together here in this lengthy one? Because there are quite a few of them being hidden in here, among the dots here. So it looks like this is 100, but the rule here says, the rule we recognize so far says each term value equal to the term position, in the indexed position. So it looks like here it has to be 100. That's how I have the 100 for the end letter. Okay? All right, so now this means once we formulated our summation, then the work is going to come a lot faster. Without adding the terms, here's our sum. 100 is the number of the number of terms. I am going to multiply with 101 because this is n plus 1. This is your n right here. And be careful. I use a capital N in this lecture, but many textbooks, see, this is capital N. I use capital N, but maybe your assignments or many textbooks use a lowercase n. There are some textbooks out there using letter K. The point is just whatever letter that is, it's just indicating an ending point or how many terms there are. Okay, we're all now living in a world of using variables, using letters to represent a count, a number, a value. Okay, we're dividing that here by 2. So 100 times 101 divided by 2. Okay, 100 times 101 divided by 2. So 100 quickly cancel with 2 because it has a common factor, and that leaves behind 1 in the denominator, and there's 50 here. So it's actually a 50 times a 101. Now your calculation can go a lot faster. Okay. So that gives me what? 5,050 after multiplying 50 with 101. Okay, and that's how we find the answer to this problem. So the challenge in this problem is that, we started out with a sum where it was not written in summation notation yet, and then we have to be able to identify a couple key things right here. A couple key things as in what's the formula that determines the value of each term so that we can put it here. And of course, we always start with term 1, so we don't have to worry too much about that. So the first key thing is to recognize the formula that stays in the sum, because that formula decides, this quick little rule to determine the value of the term, of each term right here is what decides which formula we're using. And then we have to be able to identify how many terms we have by usually and very commonly looking at the very last term like that. So looking at the value of the last term tells us how many terms there are in the whole term right here. And I'm only saying the word usually because here in all of our cases we're learning, we will always start out with 1. But in other contexts, where in other applications, these sums, even the summation notations, don't always start out with 1. It's just a reminder from algebra, okay? And so now that's how we're doing that problem right here. So let's look at part B. All right, so part B, the sum looks as following. Now, 1 plus 4 plus 9 plus 16, and I don't know how much further it's going to go. The last term has value 144. Okay, and so now with a sum like this, let's calculate the total, the final sum, but without adding up all of these. Of course, anyone viewing this video knows what terms are being hidden between these horizontal dots right here, but that's not the point of listing out all the terms. The point is, how do we write it down? How do we calculate the final answer? But in order to do that, we need to know how to recognize this in summation notation. So it looks like each term here, term 1, term 2 is there, term 1 is here, term 3, I equals 3 is for that. So it looks like the rule here, the rule to assign the value for each term is an I square. Okay, so that helps us decide already. That helps us decide that this formula will be the most and the only appropriate one in our case here for this problem. Okay, and now, and then of course we will always start out with 1. We will usually start out with 1, and the last term here, it looks like 144 here is at the 12th term. Because 144 in the rule we have recognized these are all the square on the index. So what 144? What perfect square is this? So 144 is the perfect square of 12. It's 12 squared. That's how I know that the last ending index there has to be a 12 like that. And so now we have everything we need in order to use the quick formula to bypass adding up all the terms here. Okay, so with this, we know, and knowing that we have 12 terms, so I'm going to go 12 times 13, because 12 plus 1, times, that's 25, because 2 times 12 is 24 plus 1, and that's how I got this. Okay, and I'm dividing this by 6. All right, and then now you can, quick observation in math is telling me that 12 cancels out perfectly with 6, right? And leaving me a 2 here times 13 times a 25. Okay. All right, so a final calculation here gives me 650 by just multiplying out all of these values like that. Okay, and so again, you can always pause the video and double check me with my calculation here, and triple check me by doing an actual adding up the term to see if we, but at this point, if we actually adding up the term, there's always a likeliness that you would make a typo somewhere, and that will ruin your answer for this, making some answer that does not agree with this. Okay, but you're always highly recommended to try out different directions to learn that to find out that whatever you learn here is, to bring the best purpose for us. Okay, so let's look at another one. So in part C of the example here, let's look at how about 1 plus 8 plus 27 plus 64, okay, plus, and we keep adding until we reach the last one here is 1,000. Okay, so we need to find a sum without adding all of these, because first of all, we don't know how many terms there are. Of course, it's always starting, this is term 1, so I equals 1 is here. Terms 2, so that gives me I equals 8. Terms 3, I equals 3, that gives me 27 for the value of the term. So it would be the best idea to rewrite this in summation notation so that we can recognize all the details we need in order to, boom, jump into the correct formula. So it looks like as a pattern we have recognized so far, and let's check to see if it's also agree with us. Is this fourth term I equals 4, but the value is 64, so you start having something in mind. Okay, so see if you agree with mine right here. But I see each term here has to be an I cube. So I cube is the rule to regulate, the rule that regulates the value on each of my term here at any position. Okay, but now, and of course it starts at term 1, but what's the last term right here? How many terms there are there, and who's the last term? Well, yeah, the last term is 1,000, that's the value, but which position is this? It looks like, so what cube is 1,000? 1,000 is a perfect cube of what? It looks like it's perfect cube of 10. So 1,000 is 10 cubes. So that means this is a summing from term 1 to the 10th term, or there are 10 terms, okay, where each term is on value I cubed right there. All right, and so now once we recognize this formula, then here's how I'm seeing it. I definitely don't want to add up all the terms here. So the quick formula for that, there are 10 terms. I'm going to multiply with 11, because n times n plus 1, okay, and then I'm going to square each one of these, so 10 squared times 11 squared, okay, and I'm dividing that by 4. That's one way of seeing that. Or you can also think alternatively, you can also think of this as either way. So this is a 10 times 11 divided by 2, but all squared. Either way that works for you. Okay, and so this is really 55 at all square, okay. 3,025. All right, and that is your final answer. And so you see, once it comes to this, using a very basic calculator, we can still get to the final correct answer, as long as of course, as long as we follow the correct formula, okay. But that saves us all of that efforts by adding up the terms again. Okay, so I will still put in more examples, but before we head out to additional examples, further examples, allow me to recall some other properties that, so again, these properties you must have seen. I mean, the properties I'm about to introduce here, you must have seen them back in those first day when you began seeing the idea of using summation notation. But here I'm gonna bring them back, and we're gonna utilize them and apply them in a more advanced problem, that are more suitable for the calculus study. Okay, so these are some other properties that we have seen back then in your algebra courses. Okay, so other properties of the summation. So here's the thing. Anytime you have a summation started at sum 1, and started at term 1 ending at term n right here, but each term has a fixed value, and that's what the C here means. That's what the C there means. Okay? And so instead of being some formula, instead of being some rule that's regulated by the I, some rule that's indicating the term values dependent on the I, instead of that we have simply just a value other than I. Okay? That means it's a constant term on each term. So here, think about it. If we're summing from the first term to the nth term, first term is C, second term is C, third term is C. No matter how far we go for n terms, it's all C. So what do you think this final sum has to be? Okay, so it's quickly just, this is going to be just Cn. Okay, so there you go. So 1 short because there are n terms, and C times each term, n terms, but each term is a C value. So n times of the C, that's why it's Cn. Okay, and so in short, we can write this. It's a quick work to derive but what we have concluded now is that this summation will always be c times n. That's one property that, one among the other properties that you have seen it back then in your algebra course, and now I emphasized them here again because we will be utilizing this a lot. Okay, now, so a quick demonstration here is as following. It's a quick little informal example over here. That's why I'm not even going to name that. Think about I equals 1, but we go 1,000. Okay, and each of your term here is 5, for example. Or maybe I'm going with too nice value. How about a 0.5? A 0.5. Okay, it's a constant, and it's a constant. It's completely independent with the I position. So every term is a 0.5 plus 0.5 plus 0.5 plus 0.5 all the way to the 1,000th term. Okay, so this final answer here is adding up all the terms. Without adding all the terms, but will give us the sum as following. It's going to be 0.5 times 1,000. Okay, I'm a little short in space here, but 1,000 times 0.5, it gives me 500. That really is 500. Okay, adding up 0.5 1,000 times. Adding up 0.5 1,000 times. That's another way of seeing it. And that reinforces this formula, that quick little formula right there. It's another formula. You can also see that as another formula to bypass adding up all the sums right there. Okay? And so another one I would like to show is that. So now, yes, you have a summation, and each term is regulated by the I index. Okay? Just like that, from I to some n. Each term, that's what the AI is for. The value on each term is regulated by the index I. But now, before we worry about the actual the formula or the actual rule that regulates regulate the value of the A, at least one thing we know, each term has a coefficient C, a constant coefficient C. So this C part right here, pay attention, it's C times A sub I. So the A sub I part is the part that's dependent, that's generate value depending on where your index position is. But this C is not dependent. This C is completely independent. So in other words, here's how I'm writing it. A1 is a term value at first position, but multiplied with coefficient C. Okay? A2 is the value of the term at second position, I equals 2, but it's multiplied with a C, because that's what it is right there. That's what it says right there. And then A3, whatever the term value is, but we will multiply with C again, and it's a summation. So we're adding, and we keep adding until we reach the last term AN. Okay, so the A part, the AI part is the part where the value changes depending on your index position, but the C constants remain the same. The C constant coefficient remains the same. So in that way, think about it. Isn't it obvious that C now all of a sudden becomes the common factor throughout all of these terms here? So we can pull out that, and mathematically we have remains in the parentheses is here A1 plus A2, just the bare values of these various different terms here. A1 plus A2 plus A3 plus so on and so on to the last term. And so how do we rewrite this in summation? This is the same as a summation of only the A sub I term from 1 to n, and we leave the C term in front. Okay, and so now as a something to remember after all of that quick deriving work right here, what I see now is that this here means we can bring the term in, the constant coefficient in front of the sum, and only leave the sum involving the terms that strictly the terms that dependent on the I index only. So we can always pull out coefficient like that in front of the sum. Whatever we get for this sum, we're going to multiply C in as the last step. That's what it says again. Okay? All right, so that's another property, and go ahead and note that on your own, because I'm going to have to erase this and to make space for my next formula as well. And now this is another one that was introduced in your early days when you began knowing about summation notation right here. But anytime you're looking at a sum where each term comes from two separate terms, okay? Either add or subtract. So AI plus or minus BI right here. So the parentheses I'm using here is to group. This is one term already, but each term of your sum comes from two separate terms. Okay? So quick demonstration, for example, situation like this can be seen through the case as following. Your formula or your rule that regulate the term can be an I square minus 3i, for example. So there's two terms. There are two terms. I mean, each term here has a formula already, but the formula has two separate terms, and they're both dependent on the I, and that's what this is for. Okay, and then summing from 1 to n, for example. Okay, so we can have a sum like this where each term already containing two subterms. All right, and so now the rule says we can separate this out as two separate terms. One summation for a sub I and one summation on all the bi term right there. And then if they started out adding, then here it's adding. If they started out minus, then it's subtraction between the two summation in that same order, in that particular order, A first, B after. Okay, and that's how it is. And so in that quick demonstration I've had earlier, if the formula to determine our term, each one of there is a I squared minus 3i, for example, and unfortunately we're given a sum like this to work with, where each term, the value on each term is determined by I squared minus 3i. It's completely dependent on the I. But now we can turn this into the sum of the I squared. So now it's easier to recognize that sum, and then minus the sum of the 3i. So these are all, see, this is ai, and this part right here is the bi right there, and I is from 1 to n. Okay, and so now, and we will get further into this kind of problem. Here I'm just reminding anyone about these other properties that we have learned earlier days when you began seeing summation notations. Okay, all right. So now let's look into example 3 right here, and this is where we can start. And each example, as I go to higher examples, and the level of challenging keep rising and rising like that. Okay, so again, example 3, I'm using the exact same instruction. We are looking at calculate the sum without adding the terms. All right, so calculate the sum, or the following sum. All right, without adding the terms. All right, we want to calculate without adding the terms. Okay, so the first sum I'm giving here is a summation of 4i minus 3 here, and we're starting at first term to the n term. First term to how about just 10th term. All right, so now this is how I see it. Well, writing down the terms, this is not the required part, but once again, I just want to give extra clarification and explanations here. See, each term in our sum here, in our lengthy sum, each term is determined by a formula, a rule. The rule here says at the I term, we're going to 4 times the I term, 4 times I minus 3. And that's how we regulate the value on each term. So say, for example, when I equals 1, first term gives me 1 times 4 is a 4 minus 3 is a 1. That's first term. So this is the value, and this is the term position. That's hopefully I keep clarifying the meaning of the summation notation, so that it saves you from going back and review all the way to ultra basic stuff. Okay, and then we're adding, because this is a summation. First term already nailed down. When we're at term 2, then this is 2 times 4 is 8 minus 3 is going to be a 5. Like that. So term 2 has value 5. So that's what the formula here is for. The formula here allows us to come up with the value on each term. The formula here regulates or determines the value on each term at any particular ith position. Okay, but now, and so term 3 now, it gives me 9, okay, and so on and so on. And then we want to run into the last one here. So at term 10 right here, it's going to be 37. Okay, it's going to be 37. All right, and so this is I equals 1, I equals 2, okay, I equals 3, and so on. This is I equals 10. So in the end, see, I cannot write down all the terms, but at least I know I have 10 terms. Okay, so here's how we can quickly find the answer without adding up the terms. So this sum, utilizing what we've learned earlier about the different properties right there, this sum, at least I see we can break it down because there's each term is a combination of two subterms already. There's a 4i and there's a 3. And so here I can write this as a 4i summation just on the 4i terms, where we're summing from 1 to 10 and then subtracting out the sum on all the constant term 3, where I from 1 to 10. Does this look familiar to anyone? Feel free to pause the video and to think about what familiarity that I was just now talking about. Okay, and so now I can quickly see that this term is the same as, or maybe I should write it in the next line right here. This is just 3 times, and how many terms there are? 10 terms, so 3 times 10. So that can quickly be found right there already. I utilized that one of that property where we had the summation of the constant term. That's what it is. Okay, and allow me to skip the index starting point and ending point here. So that expectedly 30 right there. So this is, you see we have constant coefficient 4, because the I part right here is the part where it needs to be, where it is independent. Just the I right here is the part that's independent. I mean, that's dependence with the I index position, but the 4 here, no matter at what term, is always going to multiply by 4. So it's a constant coefficient. This is the constant coefficient. Okay, it's coefficient. So now I can factor out that 4 out front and leaving just the I from 1 to 10. And now we are very ready right here. So now it's surprisingly turned out to be a simple sum. It's a summation of all the I terms from 1 to 10 right there. Okay, but once we've had that term down, we got to multiply that result with an extra 4. Okay, so now on my next board, so now I'm looking at that summation there was 4 times, so now it's going to be 10 terms times 11, but over 2. So all of that here takes care of the 4 times summation of I right there from 1 to 10. Okay, so that's what it is, and then minus 3 times 10 from the other part of the sum right there that I had earlier, minus 3 times 10. Okay, and so now we are so ready to complete our final sum. And see, I did not have to add up the terms at all, but here, yes, the calculation does get a little lengthy, but that is simply because I add in, a lot of explanations, I believe. But 4 cancel with 2, or there are a lot of ways how you can see that. Okay, so now it's 20 times 11. Okay, that's giving it 220, but we're subtracting 30 right there. All right, so final answer comes out 190 right there. That's what it is. Okay, so now let's look at another one where I'm going to keep growing the level of challenge a little bit more. But at least up to this point, looking at the bright side right here, then you have already keep gaining better experience in handling these sums right here. All right, so how about in the following one? Right, so B here, I'm looking at a sum. How about each term is regulated by I squared minus 3i. Each term value is regulated by I squared minus 3i plus 2. Okay, where I equals, I is going from 1 to, how about just 10 again. Okay, or maybe 10 is a little too much, I just use some number that's easier to follow. How about just 5 right here? 5 terms. So think about this. Okay, and so we don't. So first term when I equals 1, we're looking at, so that's 25 minus 15, that's giving me 10, that's plus 2, so first term is already a 12, okay? Second term when I equals 2, okay, then I'm doing my incorrect math. Okay, first term when I equals 1, that's a 1 right here minus a 3, okay, and so that's a 0 right here for first term, that's a value, okay, that's a value for the first term. And then when I equals 2 right here, all right, so when I equals 2, that makes it 4 here and minus 6, and then plus 2, okay, that's another 0, okay, but then when I equals 3, okay, and see, it takes time, it also takes time to write down the terms, that's why I'm writing it down here just for you to understand that this work here is optional, but this means we have a lengthy sum like that. So that's going to be 9 minus 9, okay, and that's leaving that out, cancel out, so that's a 2 right here. So we start having some non-zero value term right here, and then we're going to keep going on, okay, but we definitely, so when it's 5, when I equals 5, the last term right here, I skip term 4, and the last term when I equals 5 right here, then that's 25 and then minus 15, as I was saying earlier, and I mistakenly had that earlier, but we had a 12 right here for the last term like that. So 0 for first, second is also a 0 for the value, third term is a 2, and fourth term I didn't write it down. So we don't want to add all of these. A sum like this is short, so we can quickly add, but now if we, without adding the terms, how do we get that? Because see, it's not a requirement that we have to add the terms. So now here's how I see it. The sums and the difference rule earlier allow me to break this as the sum of the I square from 1 to 5. That's one of them, minus the sum of the 3i from 1 to 5, because see, there is subtraction between these two subterms. So ai, bi, maybe some ci right here, okay, and plus, and then there's a sum of all the constant terms, 2, from 1 to 5. All right, and so in that way, now that first term is so trivial. That first term we can immediately throw in the formula. It's going to be, there are 5 terms here, so I'm writing that as 5 times 6, okay, because n times n plus 1 times 11, because 2 times 5 plus 1 is 11 divided by 6, okay, and you can see that eventually the 6 will cancel, okay, minus. Now this one here, I can bring out the 3 and leaving that as a summation of all the I terms here, and we will get to that in the next step, okay, from 1 to 5, and plus, now it's 2 times, and I don't think I need, so that here is simply a 2 times 5. 5 terms, each term is 2, okay, and so now in the next step on my other board, all right, so the first term gives me 5 times 11 after canceling out the 6 away, minus now the 3 times the I, so it's 3 times, that's 5 times 6, okay, over 2. This comes from, that here comes from the summation of I, where from 1 to 5 like that, okay. And then, so just a quick explanation of what's going on so far, and then we're going to subtract, we're going to add 10. All right, so it's 55 here for the first one, and then that cancels, okay, give me a 3, so 9 times minus 45, that's giving me a 10, and plus 10, our final answer is a 20. All right, our final answer is a 20. All right, so that is part B of the example. So you can see how we can effectively utilize and blend all the properties we have learned together along with the 3 important formulas I've introduced in the very beginning of this lesson right here. All right, so let's look at, how about this, more into this. So let's look into question C of this example, part C of this example. So how about 5 plus 7 plus 9, okay, plus etc. plus 23, okay? That's the worst nightmare so far. So far this becomes the worst nightmare in a sense that we don't know the summation formula. We got to recognize that. We got to recognize the term by term summation formula, and then we got to find out how many terms. Of course, this is term 1 right here. This is term 2, I equals 2. Okay, term 3, so we need to find a regulation for that. Okay, for each of those. And then we have to find out what is this and term right here. So what's the and value? And that's the challenge part right there. So I can see that each term is a jump by 2, is an add 2 from the preceding term. So 7 here is an add 2 from 5. 9 here is an added 2 from 7, and so on. So that means my sum here has to be, my summation has to strictly be, okay, some 2i right there. It has to be some 2i plus some value. It has to be some 2i plus some value k right there. So think about it. At the value when I equals 2 or I equals 1, whichever you choose right here. When I equals 2, we had 2 times 2 plus k, and that was at this I we had 7 right here. So we can quickly find out that it's going to be 4 plus k equals 7. That's because I'm laying down all the math here, but now quickly k, okay. So k is 3 right there. All right, so now that means our formula here is a 2i plus 3 in the formula. Okay, so that's how I can quickly find out the formula that determines, the rule that determines the value on each term right here. So we got one heavy part down, but how many terms are there? Meaning we got to look at the index. We're going to have to find out, discover the index of the last term right here. So 23 is the value, but it needs to be the 2i plus 1. So at what I value, at which I value, what's the index value here that's give us a term at 23? I mean the term value being 23. So it's just a simple solving equation right here. Minus 1 both sides, giving me 22 equals 2i right there. So now needless to, very quickly we can see that I has to equal 11. So that means this whole term right here, including all of those hidden ones, right? We're looking at 11 terms. Okay, so now with all of that extra work right there, now we are ready. So once we recognize our term, it's again, each term here is a sum of 2 other subterms. And so now we can break it down as, okay, there's a 2i summation on the 2i plus the summation on 3, okay, and I running from 1, summing from 1 to, this sum running from index 1 to index 11, I equals 1 to 11, okay, that's how it's done. And so in the next step, the first formula here, we can pull out a 2, and leaving it just the simple, extremely recognizable summation of all the I terms from 1 to 11, okay, and plus, now this is already so easy to recognize, utilizing the rule, the property we've learned earlier. So now it's 3 times 11, okay, and then the last one here, now when it comes out to this is just 2 times of 2 times, and then I'm going to produce 11 times 12 divided by 2 right here, okay, and then plus 11. So this 2 cancel with that 2. 11 times 12 right there gives me 132, and then plus 11 right there. Okay, plus with that extra 11, I need some space to write it down. All right, so it's 143 as our final answer for that. All right, so nice and short, the challenge part here was that we got to recognize the formula, but once we recognize the formula that decides the value on each term, then we should be able to utilize all the rules here together. Okay. All right, and so we are now ready for getting into example 4 in our current lecture here about those summation problems for calculus. All right, so let me now spend some time writing it down. Example 4. and we would like to. So instead of doing the calculation this time, we're going to look into a different direction where we apply our understanding about the summation. So I want to write the final expression. Okay, I want to write the final expression of or how about write the final expression in terms of capital N for the following sum. All right, and so at very first sight, when we're having a look at this instruction of the example, then it looks a little hard to understand. But allow me to write down the first sum I'm given here in part A of our current example, and I will start explaining what it means by write the final expression in terms of n, and what specifically is n. We will get to that. So how about part A right here? So here we are given the following sum. So this sum here is a summation, okay, summing from first term where indexed from 1 to n. And so in our experience by far up to this point, so this capital N is the number of terms in our sum. And so our sum is, each term of our sum is determined by the formula as following, 4i minus 3. Okay, and so that's what this capital N means right here. So in terms of n basically means what this sum right here currently expressed as a summation notation. If we would have to write down all the terms from the beginning to the end right here, then there will be a way to add up all the terms without, there will be a way to find the final sum, but without adding up all the terms. So for example, again, this is not a requirement, but let me just do a quick demonstration. For first term when I equals 1 right here, this term, the value for that first term is going to be 1, okay, and then in the next term it has to be, so when I equal 2, right, and that's going to be 5, right, and the next one here is going to be 9, and so on and so on, okay, and so on and so on. But see, we're just talking about generally when the sum here ends at some n term. So at the n term, we're looking at generally sum for n minus 3, okay. So n could be 1,000 terms, n could be 100 terms, or n could be only 4 terms or whatever. But the idea now is that without adding up all the terms right here, what is the final expression? Okay, so we don't want to add all the terms here from one by one because we don't know where that n stops at. Okay, but in the end, so if we really are adding up, if we really find the sum of all these n terms right here, then what is that final expression? And that final expression there is needless to say, or makes sense now to be in terms of n, the number of terms. See, n has, in our experience up to this point, it's the number of terms, okay, being described, being indicated or represented in this summation, the representation right here. Okay, and so now that's the idea again. And so now it is and you can see that as I keep, raising to the next example, as we keep heading into the next higher example, and each problem becomes more challenging and more challenging. But that's the whole intention where I put all of these, the advanced enough problems so that calculus students can have some good hands-on experience with these sums, so that it will bring into your calculus work either sooner or later. Okay, and so now utilizing our properties where we can, because notice that each term of our current sum here is a combination of 2 subterms. Okay, I'm calling that subterms just simply because 4i is one individual term on its own, and this 3 right here is another term on its own. So these are 2 separate terms being connected by the subtraction sign. Okay, so, and unlike the previous examples where we had a finite ending point right here, but here we just have some general ending point. And that's why the problem can only leave us a final expression instead of an actual final calculation. Okay, and so now the first thing I can do now, I am going to break this summation into two separate ones. So one of them is a summation on the 4i summation, and then the other one is just on that constant 3, where I is running from 1 to n. That came directly out from the rule, one of the rules that we've written down earlier. So it's a rule that allows us to break a summation into two separate summations on the two separate terms right here. And these terms came out from that. And particularly here it was a subtraction. So I have to write the subtraction of the two sums here in the order that was particularly indicated from the beginning. Okay? And so now we're going to continue. And so now we're going to continue applying our further understanding of, and we're blending in the other properties in there. So if we're looking at that first sum right here, then it is just simply the I coefficient. I mean, the 4 here is a coefficient, but the I is the only formula that's dependence. This I right here is the only part that's depending on the I position, the I index position. And so in other words, I can bring that 4 to the front of our sum as a common factor. That means 4 times of whatever result that would come out from the sum of all the I terms, where I running from 1 to n, to some capital N. Okay? And then now I'm going to subtract, and then this sum here is now simply according to what we've learned earlier. Then now it's going to be just 3n, 3 capital N. And so now we slowly displaying some terms, we slowly coming to the expressions where we start involving the n expression right here. And n again is the n again is here is to be the number of terms like that. Okay? And so I have to make a side note here a little bit. See, n has been my notation here for the number of terms since the beginning of this lecture, but it could, in some other times, it could be lowercase n. It could, this n here could be a lowercase n. This n here could be a k. This n here could be an r. Textbook authors out there can use any kind of variations for this, any value. So in that case, if you would see a problem like that where it wasn't this n, and it has to be like either a lowercase n or a k or an r whatsoever that people can come up with. It's just a variable indicating that the number of terms we're doing here. All right, and so now in this way, according to what we know previously, that we have already known, then this sum here is going to be capital N times n plus 1 in the next step over 2. But don't forget, that is only for the sum without a coefficient 4. Okay, so without a coefficient 4, this sum right here gives us this value. But now with the coefficient 4, we need to multiply that in. Okay, and then we're going to subtract 3n. So now at this point, at least as far as the final expression that's in terms of n, this is the one. Okay, because this final expression tells us that, hey, if we had if n is like 100 terms here, then all we do is 100 times 100 plus 1 over 2, and minus 3 times 100, and multiply with that 4 in the front of that term right here. Okay, it's a quick formula here generally to describe any time for any n value given for any number of terms right here. Then we can quickly get the final sum by this expression right here. Okay, that's what it means by write the final expression. This is the final expression in terms of n for the following sum. But here's the thing, I'm not quite satisfied with this final expression in the sense that we can still simplify further. So now I am going to simplify that 4 with that 2 right here, and that turns the first term into just simply an n times n plus 1, okay, and then minus 3n. So this one right here can be regarded as a one final expression in terms of n right here. Or alternatively, we can go even further. So on my other board right here, we can write that as, we can distribute out the n factor, so it's going to run into an n square, okay, and then plus n, that's after multiplying, this is all that here, after multiplying out the n times n plus 1, distributing through that capital N, and then we're going to subtract 3n, okay, and so our final, that I'm quite feeling satisfied with this one here, is an n square, okay, minus 2n. Okay, so that's the final and also simplified expression that represents this sum here, right? And express everything in terms of n, the number of terms for our current sum. Okay, and so once you have the idea of this, part B of this particular problem is just another problem for any one of us here to try, and then we learn more experience. But that the idea now is exactly the same with this. Okay, so now before I move on to the part B right here, you see, due to the fact that the final expression now is in terms of n, completely in terms of n, okay, the number of terms. And so now it's time to let anybody know anyway. So a sum like this, that usually many textbooks would indicate that it's a sum. But the sum can be expressed in terms of how many terms there are, n terms. The sum that's dependent on the sum, whereas the value, the total, is dependent on the number of terms. So that's why usually something like this is notated as an S sub n right here. It's a sum that depends on the number of terms right there, because that's due to the fact that we can always write the final expression as an expression in terms of n, the number of terms right there. And so this is the starting out form as a summation notation, but that starting out form will end up into a final expression involving, in terms of all the n, all the number of terms there. Okay, so now let's look at part B of the example. So in our part B right here, the summation that we're looking at here is that we're looking at I squared minus 4i plus 3, and then this is a sum that runs from first term, that's adding from first term to some n term. Okay, and then again, right out from that explanation I've given at the end of part 8, and so now we can call a sum like this. Once we reach to the end and successfully get the final expression in terms of n, the number of terms, and this whole sum right here is indeed a sum that turns out dependent on the sum that's dependent on number of terms n right here. It has n terms. Okay, and so now I don't need to write down the that non-required list down the terms right here. So I'll just get straight into the problem right here. We can break this term, see, 3 subterms being involved in each term of our total sum right here. So 3 subterms, we can now break that. One of them is the summation of all the I squared terms. Okay, and we have another one that's connected by a subtraction. So here it's a summation of 4i, summing from 1 to n terms, the first term to the n term. The last one here is a summation of all the constant term, where we're adding from the first term to the n term. Okay, so now we have just now produced 3 separate summations. Okay, and all of these together, once we successfully ended up with a final expression in terms of n, that's how we call it. It's a summation value, right? In terms of depending on the dependence on the n terms like that. Okay, and so now this one here, we can now quickly use that formula we have learned earlier, the summation of I squared terms, okay, for sums running from first term to the n term right here. That here is expressed in terms of n times n plus 1 times 2n plus 1 and divided by 6. That's what happened to that first term. Okay, the next term right here, the next summation right here, subtraction, we can now pull the 4 in front and turning that into a summation of I, where I is running from 1 to n, and then this last term here is the same as 3n. Okay, all right, so in my next board right there, I'm just simply going to write down the final expression on that particular term in terms of n, and then we're going to start doing some algebra that's combined like terms with all these. Okay, so in my other board, yes, first term was n, and then n plus 1, and then 2n plus 1 all over 6. The summation of the I terms giving me n times n plus 1 over 2, but now there's a coefficient 4 in front of that. Okay, and the last term here is now 3n. So now at this point, I can tell anyone that now we have already come up with a final expression completely in terms of n. And this is again the reason why our sum in the beginning was called an S of n, like that, because it's a sum. It's a sum, and all we need to do is know the number of terms being involved, and that gets us the final sum of our beginning problem. Okay, the final sum of our beginning summation right here, without listing down all the sums here from the first term all the way to the last term. Okay, and so now, but I am not quite satisfied with this answer because it still looks, quite lengthy. Okay, so I'm going to start doing some simplification. So the 4 here is going to cancel with that 2, and it gives me and actually I am going to hold on to the cancellation here. I am going to write it as 4 times 2, but I'm gonna make common denominator because we have fractions here. So, and I'm gonna also distributing the terms like that. Okay, we're gonna multiply out the terms, foiling out the terms. All right, so the first one of mine here is going to be n times now distributing out, foiling out these two factor, the n plus 1 and the 2n plus 1. We're looking at n squared plus 3n plus 1, okay, over 6, and then I'm going to subtract. Now I want to make the common denominator, so here's denominator 2, denominator 6 here, so I'm looking at a 12n times n plus 1 over 6, okay, in that purpose to have a denominator. And then this third term, I am going to create the common denominator with that as well. So from over 1 here, we're going to turn that into over 6. So that's going to make it 18n. Okay, so we're foiling things out, and then we're making common denominators at the same time. So first fraction here, I'm now going to go ahead and distribute out. So we're looking at n cubed plus 3n squared plus n, and then over 6. And the next term here, I'm going to distribute out these two. So it's a 12n squared plus 12n. That's in one fraction over 6. Okay, and then here we're adding with 18n over 6. All right, and so now, here it's mostly just, at this point, it's just all that the basic algebra part like that. Right, now we can bring it all into one fraction, all over 6. Here's a n cubed plus 3n squared plus n, and then minus. Now be careful, there has to be some sign change here. So minus 12n squared and minus 12n, and then we're adding 18n like that. All right, so now the final answer completely in terms of n and quite simplified for us here is going to be, all right, so all over 6, we're looking at n cubed. These are like terms, okay, 3n squared minus 12n squared, okay, so that's going to become minus 9n squared. All right, and then these n terms right here are like terms, so now I'm looking at plus 7n. Okay, and so now that is our final answer. Okay, it's an expression. So this is our sum S of n right here. This is our sum. This sum right here is the final expression for S of n. It's S of n. It's the sum that is expressed in terms of the number of terms, and the capital N is the number of terms. And so now, after you've learned, have gained some majority throughout working through example 4 here. So now let me still along this way. Let me bring you into the next example, where I call that example 5, similar kind of problem. But now I designed these next problems in example 5 here for a different purpose right here. All right. So example number 5 right here. So we still want to write we still want to write the final expression in terms of n for the following, any one of the following sum that I'm writing on the board here. So part A, my summation is going to look as following. It's a summation, summing from first term to the nth term. Okay, and this is for some terms being ai, a times I, that's what it means right here. ai, a times I. Instead of 3i or 4i, no, it's ai, generally, some a times I. Okay, so I'm starting to mention that. And then over n square. All right. This is the part where, over my time teaching in many years past, in the past, when students get to this point, a lot of time, right at first sight, start getting students hung up, in a sense that this n right here is a little confusing because it is the same n with this. Okay, it is the same n value with that. If here it's a lowercase n and here it's also a lowercase n, and then there's the a. So the reason that got students of mine hung up before is because they got confused and they worry about what exactly, how should they treat that n right here, that n square expression in the denominator, or generally speaking, we got some n expression. Okay, that's the variable is the same variable as that. So here's the thing. Those people who think that way, you're overcomplicating the problem. The idea of a summation now is that we have done we have done many problems enough up to this point. I can now loudly tell you that the summation is, the final n expression, the summation is only depending, only worked out on that part where it has the I right here. Anything else that non-I, anything else that's not the I part right here, you can treat that as a coefficient. You can treat that as a coefficient. So this is what I mean right here. So now I realize I made my board a little too ugly. So here, the same summation, but as a fraction. Now you can see that we can put a over n squared as a coefficient times I. Okay, so really this I is the only part that matters because the value of the term will change depending on where the position is, where which term we're at. But the a over n squared will remain permanently the same. So think about it this way. First term will be 1 times a for whatever a is over n squared for whatever the n squared is. And then next term is going to be a again over n squared times 2, because this is the only part that's dependent on the position of your nth term. And then plus a over n squared times 3. Okay, so now you can recognize the elements in a formula like this. You can now clearly recognize the elements where it's changing depending on the I position, and then the elements that remains the same right here. Okay, and so in that way, the reason I hope I mentioned that clearly enough and in detail enough, because now the reason I mentioned that in that way so that now you can treat all that, the whole a over n squared here, as a coefficient in the way as the way how the operations here is indicating. So a over n squared as one operation. So the good usefulness of that, and I don't think I even have to jump down to the next line. It's right here. A over n squared can be pulled out in front of the sum and become just a coefficient, a common factor in front of the sum. And now your sum shockingly or surprisingly becomes just this simple. And now in the next step, we can just find the final expression of this summation on I right there. Okay? All right, so that means now I'm ready for my next step and getting pretty excited about this. So a over n squared remains as a coefficient. But that entire sum where I underline with the square brackets underneath that here, we already learned the formula for that. It is n times n plus 1, okay, over 2. And I did say this many times. Within this problem, this n and that n is the same variable. It's purposely, there. I mean, it all came out because of different kinds of problems we're dealing with out there. Just the first thing I try to clear out for anyone viewing the video is that it's the a over the n squared expression here. It's just not involving directly with this changing parts for the I right there. That's why we were able to pull it out front. But in the end, once you come to your final expression in terms of n, then it does matter a little bit. Now we can cancel the n. It matters in a good way. We can cancel the n away. So now that n cancel with this n, leaves one n left. So now we're looking at what? A times n plus 1 in parentheses over 2n. So now this is the final expression here that it's in terms of n. This is the final expression for this sum right here. Okay, and that sum, yes, once again, it's called the sum S of n. It's a sum that depends on the value to come out, depends on the number of n, the number of terms. But then it also depends a little bit on whatever the given value for a is. Okay, but there we go, we found it. All right. And so now let's look at another problem. So all of a sudden it looks challenging at first, but in the end, once we have a thorough understanding of the expression, okay, the relationship between the n that's involved in each of your sum term and then the I part right there, then things can move on a lot easier. So how about the problem we have is as following: a I square over n cubed, okay, and then I is running from 1 to n. And yes, this is a summation on n term, and this is problem for part B right there. Okay, and so now again, just similar, very similar, or you can say it's the exact arguments I've made earlier. I can see this, each term here is an a over n cubed times I squared. So now, right in that explanation I've given earlier, the I squared is the only part that's changing depending on where your I term is. But all of these stays the same. Or in other words, that is all in one package here, the whole a over n cubed. It's a common factor. Okay, and so now the bottom line is any of the problem like this kind right here, all you have to do is be able to identify the changing parts, the part that's changing depending on your I position, and everything else that's not changing depending on the I position of your term. You can just leave all that as one package and as a coefficient, as a common factor. Then eventually you can bring it out front as a common factor here. So a over n cubed is a common factor, and that factor is multiplied with whatever comes out from this sum, I squared, summing from 1 to the n term right there. All right, and this is another one, another easy one, the I squared. We've seen that the shorthand formula for that, the shortcut formula for that. Okay, so now I'm looking at a over n cubed. Okay, and now I'm multiplying with, so the summation that's being indicated with the underneath the square brackets here is going to give me n times n plus 1 times 2n plus 1. Okay, and we're dividing that by 6. And so now just lots of cancellation is going to happen. And actually, I'm lying a little bit, but not that many actually, but we can see some cancellation. N cancel with n cubed, leaving an n squared in the denominator. So my final expression here in terms of n is simplified down to a times n plus 1 times 2n plus 1, okay, divided by 6 n squared. This is one of them. All right, this is one of them. All right, and then in case all right, so back to what I was saying in the middle. In case that anyone is unhappy or unsatisfied with that final answer currently expressed in the other board, then we can now FOIL out. So let me rewrite that what we've had from the other board. So that this is what we currently having, and over 6n squared. Then we can advance further into the FOILing out. Okay, FOILing out those two factors right there. So now I'm looking at 2an squared plus 3an plus a, and that's all that is over 6n squared. That's another way of writing your final answer. Okay, that write your final expression completely in terms of n like that. Well, we do have the value of the whole sum of the whole s of n right here. So this is s of n clearly, all of that there. That's s of n. But so once we have a value for n, the number of terms given, we're still going to need to know what's the value given for a right here, so that we can complete our final numerical value for s of n. Okay. But now along that way, for this particular example, let me quickly design an FYT, a problem that's for students of mine and viewers out there to try on your own here. So an FYT is the kind of problem where I only write down the problem and you can pause the video and solve it on your own, get the problem done on your own, and then once you're done and resuming the video, all you do is just show the final answer, and that's it. All right, so as an FYT, but it is another problem, part of example 5 right here, but instead of calling that part C, or we can call that part C, but it's an FYT as noting for your trying. Okay, then let's write the following sum right here. Write that sum as a final expression in terms of n. So how about 2 capital N I right here, where I equals summing, where the sum here is summing from first term to the n term, to some n term. Okay, so go ahead and pause the video and have the problem done, try out, have fun, right? And then once you believe you've had your own answer expressing the final expression in terms of n, then go ahead and resume the video. All right, so now assuming you already had your video after you made some short pause right here, the final answer to this, and of course if you are a student who studied directly with me, you can always get a hold of me to clarify right here. I might make error too, okay? So but the final expression for this sum right here in terms of n, okay, is going to be n squared times n plus 1, okay, and that's all there is for that.